mainly here, but the last 2 lectures will be in the lab because we will analyze the results of some seasonal forecasting models. Let's see, but that will be decided in the very end, I think. Okay, there will be homework at the end that I present at the end of each lecture, and I expect that you do them and then we discuss them at the beginning of the next lecture. Mainly only the more difficult ones, and if there were problems, and then I will also ask then maybe for you to do them on the blackboard. They're very important part of this course, because otherwise it wouldn't make sense. We have to know that we are all on the same level. So the main textbook recommendations are the Holton Dynamic Metrology. It's a very, very nice textbook, not very mathematical, but he explains concept very nice. I like it very much. But there are so many textbooks right now in this field. Another one that is very good is Pedlowski, but the problem there is essentially the Holton you can open on page 200 and you will understand what is going on, what it's talking about. The Pedlowski is an extremely very systematic textbook, but he starts it's so systematic and introduces scaling at the very beginning that if you open the book on page 200 you may not understand what he's talking about, because everything is scaled already and you have to go back. So essentially you have to read the book from the beginning or go back to where it's needed. So all these lecture courses will be on my public directory. So you can copy this lecture, all the lectures from there. They are numbered, so this is lecture 1, lecture number 1 will be there. The reason is that there are still mistakes in it, so I'm also asking you if you find mistakes, even spelling, it doesn't matter, but more importantly, mistakes in the derivations or whatever, you please tell me, then I can correct them and then I can upload a new version of them. So that would be very nice. So the topics of the course. Let's see if I'm sure you're aware of most of the topics. And by the way, there are some chapters here that are not in these 2 textbooks shown, Pedlowski or Holton, where then I give at the beginning of the chapter, I give some recommended literature. But the basics is really the Holton. So the topics of the course will be, we start with the vorticity equation again. You have seen the vorticity equation already in Riccardo's course. You all also attend Riccardo Farnetti's course?
I have not attended the course, but I read a book, Pierre Ambert, on planetary climate.
So the concept of vorticity is certainly not too complicated. But what is important for the atmosphere and for flows is the potential vorticity conservation that we will probably derive today. You're aware of this concept too? Is this the potential vorticity? Everybody has heard about that from Riccardo's course? More or less? Yeah. We will derive this again. It will be a repetition, but I'm sure Riccardo has derived that law. Then next lecture we will discuss quasi-geostrophic motion and the thermohydrodynamic equations in pressure coordinate system, because we are mainly considering large-scale flow. That means we are not interested in really describing convection here, which maybe Adrian done in the last semester. But we want to understand the flow on scales that are minimum hundreds or thousands kilometers large. And those scales, we know that the hydrostatic equation is valid to a very good approximation. And that enables us actually to make a coordinate transformation from having the vertical coordinate z. Instead of that, we can use the pressure coordinate p. And nearly, or let's say not nearly, but many of the global climate models that are used, or even weather forecasting models, are posed in this pressure coordinate system, or small deviations from that, small modifications of this pressure coordinate system. So it's a very useful system, and we want to derive this in this lecture course too. And there are some simplification that go along with that. It's quite interesting actually. And also most of the observational data, or we call them reanalysis data because they are mixed observations with models. They're also, the data sets usually you find as vertical coordinate the pressure, not the height. So it's important to know this coordinate system if you work in atmospheric dynamics. Then we will discuss the most important extratropical waves, which are the Rossby waves, which govern the change of weather in the exotropics essentially. So we will derive their dispersion relationship. They can be free waves or forced waves. We can discuss both. And then after that we will discuss, so what makes these waves, the way we derive them, then they don't grow or decay. They are just, the dispersion relationship is real, so there's no growth or no decay. But of course, in reality, that's not the case. These waves grow and decay. And the most important growth mechanism for these kind of waves, for these very large-scale waves, is what we call baroclinic instability. So the temperature variations that eventually translate also into vertical wind shear is the main mechanism that makes these waves grow. And we derive this in a very simple two-layer model that can be derived really in a three-dimensional framework, but that's much more complicated. So we try to keep it as simple as possible. Okay, then for the time being, we leave the exotropics and go to the tropics. We study tropical waves, equatorial waves, discuss Kelvin wave. There's a very interesting wave imported in the atmosphere, also in the ocean, that is a Kelvin wave, which usually in the ocean are along the coastal lines, you know that. But the equator is such a special place that it also gives rise to these waves on the equator. And we will discuss the theory behind this a little bit. Then we will discuss the ENSO phenomenon in the atmosphere and a little bit in the ocean also. This coupled phenomenon, you know. Have you heard about ENSO? Has everybody heard about ENSO? Even the Europeans. ENSO is more important maybe for the tropical regions in America. Gives some, you know, it's a main source of predictability for longer than weather timescales. Maybe we can be able to predict rainfall in Africa or in South America based on our guess what will be the ENSO state in the next months. And so therefore we will discuss this in a very simplified framework always. Of course, it would be nice to have a closed theory for everything, but as you well know already, we cannot solve the Navier-Stokes equations as they are. So usually we can do either two things. We can use a hammer and simplify them in a way that the main purpose is to understand something, but they really just don't describe exactly what's going on. Or we can apply statistical method to analyze our data. But we don't have a theory to describe everything that we see, really a closed theory. So therefore we are using the simplification a lot. Then we discuss the boundary layer processes. Some of them, of you have done that already in Adrian Tompkins' course, I think, in the first term. what happens in the boundary layer of the atmosphere. For us, it's mainly, for my personal interest in doing this, is to derive this Ekman pumping, which essentially, in the free atmosphere, we have an equilibrium that is very important in the large scale, which is called geostrophic equilibrium, but that is disturbed at the boundary, and we get inflow into cyclones and outflow in anticyclones, and that leads to this Ekman pumping, which can be an important process to create rainfall variations in all regions, in the tropics and exotropics. So that's the main purpose of doing this, even though I'm sure you've done this in other courses already, but we simply repeat this a little bit. Then there's also something very important for seasonal forecasting, essentially. So ENSO can provide some perturbation to climate and weather, but how does that translate into rainfall or other anomalies, temperature anomalies in other regions? So we need to discuss teleconnection mechanisms. So some of the teleconnection mechanisms we will discuss here, mainly the rainfall responses to a localized heating. Then that information somehow spreads around the globe and causes teleconnections all over the world. So this is actually one of my main interests in my own research. Then the general circulation, we will discuss a little bit what is happening if we just calculate a zonal mean and then see, because most of the temperature differences are in the meridional direction, so we can, to simplify the system, just assume that the planet is a zonal mean planet, and then discuss these kind of circulation cells that appear. Then we discuss also circulation cells that are more in the tropical regions, the Walker circulation. Have you heard about the Walker circulation? Who knows what the Walker circulation is? Okay, so somebody can learn something here. You probably also know what Sverdrup balance is. People who are interested in the ocean probably know this. But it's also important for the atmosphere. Then we will talk about the energetics. This has an energetic framework, and Lawrence, a very important, Edward Lawrence, climate scientist, has developed before, have you heard about Edward Lawrence? He's actually responsible for this chaos application of nonlinear dynamics to atmospheric flow. This complex three variable system that has nonlinear interactions and describes some of the behavior of atmospheric flow also. But before doing that, having that famous study here, he developed also an atmospheric framework, an energetic framework for the atmosphere. And we'll discuss this. Then we have a look at an interesting equation, which is the moisture budget, actually. It's also important to understand teleconnection mechanisms and so on. So the vertically integrated moisture balance will be an interesting equation to look at. And this has implications then to understand the connection between rainfall, evaporation, and the moisture, the convergence in the region. We will discuss this in the framework of the Sahel drought. And there's an interesting feedback mechanism also involved in this, which is called Charmy feedback. But that goes already much more into climate. And then we say, okay, at this point we completely give up to describe things with Navier-Stokes equations, but we want to look, can we apply a statistical tool to analyze this enormous quantity of data, observational data, but also model data. If you apply a model, a climate model, a complex climate model, that the output of that model is almost as complex as observing the real world. So there's no way you can easily understand it. So you still have to apply some methods to try to understand what's going on in your model. And one of the analysis that anybody who will work in climate, or I think, yes, atmospheric or ocean, I think, or even solid earth, I guess, is the method that is often used, a very basic method, is called a principal component or also EOF analysis. Who has heard about this method? So it's also something to learn here. It's a very basic tool to kind of try to characterize very, very large data sets which have many different modes of variability, and you try to find what are the main modes of this variability. It's a very standard technique, one of the basic ones. And then at the very end, we come back again to Lorentz. We will discuss the concept of predictability in the atmosphere. You know, unfortunately, the predictability of the atmosphere is limited. Everybody, have you come to current weather sometime? Some of you know the weather. Everybody knows from experience that even a weather forecast has a limit. We cannot predict the weather. And we have to understand why this is, because naively thinking, if the equations would be very simple, maybe we could predict for the next 100 years everything exactly, like the movement of planets, maybe, I don't know. But yeah, but weather is much too complex, climate is even more complex, and therefore that's not the case. So we have to understand what are these limits of predictability, where do they come from, and how can we measure predictability. And there comes this Lorentz model back, who kind of derived some ideas from a very simple model about the predictability. And that's it. So we start to look at this vorticity equation. And why is vorticity important? Let us just consider this, make this consideration. So what you see here is this is a model output of a model that I have used many years back, where you could store the data probably in this pen drive altogether from the simulation. It's called a baroclinic model of the atmosphere. Anyway, you can imagine that what is shown here, this 0 could indicate we are at the equator here. And this 8, this is in 1,000 kilometers, 8,000 kilometers to the north, for example, is the North Pole. And this goes from the surface to 15 kilometers height. And this model, with the model one can do many things, you can play around. In the initial state, there are only variations in the meridional direction, but zonally completely symmetric in this model. But as you can see, the iso lines here, the continuous lines here, are the lines of constant potential temperature. You know what the potential temperature is? From physics, maybe a little bit, people with physics background a little bit more, have more difficulties, but essentially, from a more physical point of view, the potential temperature is really something like the entropy of the system. So one can derive that for a perfect gas, the entropy is equal to Cp ln theta if it's just a one component gas. So there's a very simple relationship between the two. And then the potential temperature can be derived as again a function of just the temperature and pressure, like the entropy is, for example, or any two thermodynamic variables. The intuitive interpretation is that it's the temperature that you get if you get into an arbitrary level, take a parcel there, bring it to the surface, and then that's the temperature that is assigned to that level. That's called potential temperature in that case. But in the horizontal direction, any temperature difference will be also seen as a potential temperature difference. You can see this here. So it's warmer at the equator, and colder if we go into the exotropics. Of course, you know that this is the main forcing that we have of the atmosphere comes from the differential heating between the equatorial and the polar regions. So this is kind of we accept in our dynamical treatment as an external forcing. The dashed lines that you see here are lines of constant zonal velocity. So it's the velocity that goes into the board here. And you see there is a relationship between them. It's interesting. So as the regions where we have the largest temperature change, then at some point we get what we call these jets in the atmosphere, just at the top of the troposphere. So why are the lines so dense in this region here? What is that?
Stratosphere.
That's the stratosphere, right? That's in the stratosphere is characterized. You probably remember that the potential temperature can be used as a stability parameter for the atmosphere. So any d theta by dz is related to what we call Braun-Weiserler frequency.
Oh.
So a large d zeta by dz gives us a large stability. So that's happening in the stratosphere. That's a characterization of the stratosphere in this simple model. It was just imposed like that. And you see that, just at the edge between troposphere and stratosphere, you get this jet-like behavior. And in the troposphere, the fact that this never changes sign means that the atmosphere on average, in the mean, is always stably stratified. This is always positive. d theta by dz is always positive for our large-scale considerations. Of course, if we go to micro scale, we can have instabilities, convection events. But on a larger scale, that's not the case. We have always this. And this can actually be used. You know, before we mentioned we can use actually the pressure as a vertical coordinate system. This property can be used to use also potential temperature as a vertical coordinate. You can make a coordinate transformation. There's a whole theory behind using different thermodynamic variables as a vertical coordinate. This property can be used to do this. So there is a relation, as you can imagine, there is a relation between the wind shear, vertical wind shear, and the meridional temperature or potential temperature change. And you will derive as a homework actually at some point that there's this relationship here, which is called thermal wind equation. A very powerful equation that relates us whenever we have a meridional temperature change, we have to have a vertical temperature, vertical velocity shear. Very important. So let's imagine this model. There's no horizontal, there's no zonal change anywhere, just meridional change. And we put a very small perturbation somewhere. In this model you can wait a few days, integrate the model if it's not crashing. And then after about 5 days or something, if we take a look now, a different look at it. This is now, we look now at a domain. This is now the X. This is actually, this model is zonally symmetric. So whatever comes in here goes out there. You can probably see this. And here is again the Y domain. And we here just look at the surface. And what is happening is within a few days in this model, spontaneously, we get this huge, what we call cyclones and anticyclones developing because of this baroclinic instability mechanism that we will discuss later on. So they develop spontaneously. There's nothing, you don't have to do any initial condition that resembles this. It can be any small random perturbation that you put, they will develop these large-scale systems with thousands of kilometers in diameter. This is a high pressure. You see the surface pressure is 1030 hectopascal, and a low pressure. And they move around in this model and develop. And what they do eventually, of course, is they transport the aim, if you want to, is to transport the warm air from the equator to the pole, and the cold air from the pole to the equator. That's kind of they mix the atmosphere, and by doing this they gain also kinetic energy. So they transform this potential energy in this temperature change into kinetic energy eventually by letting the warm air rise and the cold air sink. We will also discuss this later. So it's a very interesting framework. And you see that the concept, you have heard about the geostrophic balance, right? So the winds tend to blow on the large scale along lines of constant pressure. So the winds will blow around these lines of constant pressure, high pressure and low pressure. So the rotation, that tells us already, rotational winds will be very important here. Much more important than actually divergent winds, even though, but those small deviations are important too. So let's go to the basic equations for this that describes the horizontal motion, for example, around this high pressure and low pressure systems. So we are discussing about the large scale flow. So in principle, we want to describe the flow on a sphere. And of course in models this is done properly. There are metrical terms that appear if you pose the thermohydrodynamic equations on a sphere. There are additional terms. They don't look like the equations in Cartesian coordinates. But there is for our theoretical description, it's enough to ignore most of these metrical terms. So essentially, when we see a d by d, or dx, that always means we are thinking about something radius of Earth times cosine latitude times d longitude. If we see a dy, that means always radius of Earth times d change of latitude. When we see a dz, that means we are looking at the direction or local vertical. It's just a change of the radius. Of course, the change of the radius of the Earth, not of the Earth, of where we are with respect to the center of the Earth, is always considered to be small with respect to a constant value that is 6,600 kilometers or something like this. Our treatment is mainly in the troposphere, so it's just 10 kilometer perturbation. So we can keep this R just as a constant for our consideration. We don't have to worry about varying this, even though it's changing, of course, if we have vertical motion. And then we have this new term for our large-scale flow, which I'm sure you have derived in Ricardo's lecture. What are these two terms here? Coriolis parameter, that's the Coriolis force, or Coriolis acceleration in this case. And the formulation is 2 omega rotation angular velocity of the Earth times the sine of the latitude. And there are some additional terms of this Coriolis parameter, another Coriolis parameter multiplied by the vertical velocity that I ignored. So this would be the equation actually in Cartesian coordinates. That to a good approximation we can apply even on the Earth sphere if we don't go too far from some base point that we define. That will particularly concern later on in our derivations how we express this Coriolis parameter f. because in our theoretical treatment we will just assume maybe to be a linear function of y. So what are these terms? This is the how we call this term? Advection. Generally, these are the advection terms. We have said this is the Coriolis term, and this is the, what is this? Pressure gradient force. So there are other terms we have obviously dropped. For example, frictional terms, for the time being, we simply drop in our analysis. In principle, we could add them. Later on, sometimes we will just add them, but most of the time we will ignore them. But of course, for the planetary boundary layer, they will be important, so we will keep them. But for the free atmosphere, let's say this is a good description of what is happening in terms of the horizontal equations of motion. What is how does the vertical equation of motion look like? It's just a hydrostatic balance. Then the vertical, we just have a much simpler equation. So we have dP by dz equals 2 minus rho g. So that's our vertical equation of motion, which is not an equation of motion anymore. This, of course, also means that we cannot use this equation to evaluate any vertical motion anymore. So does this equation mean, what do you think? Does it mean that the vertical velocity is 0?
Vertical acceleration.
It doesn't mean that, right? It just means that the terms related to the vertical velocity acceleration terms, for example, are so small, probably 10 to the 8th or something like this, times smaller than this, that we can really ignore them for large-scale flow. If we go, at what kind of size, if we have a numerical model, let's say, of weather or climate forecast, what is the size where we would have to take into account perturbations from this equation and maybe have a non-hydrostatic equation? Do you have an idea?
Under 10 kilometers.
Under 10 kilometers, that's right. So you can, if you make a scale analysis, you can estimate that if you go below 10 kilometers of scale, really, you may have to consider, even though this may still be valid, but in the zero order, but in the first order, you definitely have to look for some kind of vertical acceleration of our parcels. But for the large-scale flow, this equation is a perfect law, so we can use it. How do we derive from this equation the vorticity equation? From this momentum equation, how do we get the vorticity equation? Kind of cross derivatives, right? So that we have to do a d by dy of this for the first momentum equation and a d by dx here, and then do the difference. Because that gives the vertical component of the vorticity, which is the most important for our consideration. And it's the only one actually the only component that we can fully evaluate with these two equations. So this is an equation for the vertical component of the vorticity, which we can derive from the horizontal velocity components. It will be an exercise for you, a bookkeeping exercise, to derive then this equation here. Of course, we have to use the product rule of differentiation. Yeah. But in the end, we get this equation here, which has many terms. So there's an advection term again. There's this term here, which we'll discuss now. There's this term here, there's this term, and there's this term. So many terms, complicated, of course, complicated stuff. But it turns out, for our large-scale considerations, there's one very basic mechanism that is actually dominant, which we want to understand. So you can combine here something again and make it an equation instead of an equation for the relative vorticity, which is thus derived by our flow. Instead we consider an equation for the absolute vorticity, so we take into account the planetary vorticity that is defined by F in this case, in this simple case. That is possible because this is just a total derivative of F. Now, F is just dependent on Y. Unless the speed of the Earth rotation changes very quickly, but this is not. This is definitely not the case, and we don't consider that. So there are several terms here, and thank God, not so many are very important. So the first term here, and it turns out this will be the most important term, is called the divergence term sometimes. And the physical interpretation is really not much more than if you see an ice skater and he rotates and then he brings his arms closer, he reduces the the radius of his arms, then he spins up. So the angular momentum conservation, that's described by this term. Only that there's with respect to small scale motion, there's an important asymmetry here, because for small scales there would be no F. There would be a complete symmetry between cyclonic and anticyclonic rotation. But for large scales, it turns out there will be a dominance here of the F in this term, and then we have to evaluate what that means for the vorticities. But in principle, this is just angular momentum conservation here. This term here is also an interesting term. It's called twisting term. It turns out for our large-scale considerations, it's not important. This term means that we have a rotation axis that is located in the horizontal that can be twisted or turned into the vertical direction. Actually, this term we discussed last year in current weather several times, tornadoes. This term is supposed to be relevant for development of tornadoes, because they may initially form horizontal rotation that is then turned due to vertical horizontal shear of vertical velocity into a tornado type variability. But for us, it turns out we don't have to consider this, but we will verify this with a scale analysis soon. This last term here is a real production term. It's called sonoidal term. And this would be important, it turns out, for land sea breeze, generation of land sea breeze. So things that you observe in Trieste and other sea places during the day and during night. It means that lines of constant pressure and lines of constant density, that they have to intersect. It also turns out this term, even though it's the only real production term here for vorticity, but for the large scale flow, it doesn't play such a big role. Okay, so we can, yeah. It's an exercise, but it's truly, you can see this, that you can write this term also just as a cross product, where the nablas are just the horizontal vectors, the horizontal nabla operator. So how do we see which term is really important here? We insert numbers. This is always good. We get some feeling about numbers. We want to know the scales that we are talking about. Okay, let's start with the horizontal velocity scale. Okay, let's say the scale analysis ideally would explain things. Unfortunately, we may be able to take explaining things, maybe the horizontal, the vertical extent of our flow, the height of the tropopause, maybe we can say about 10 kilometers. This is a quite safe guess. Horizontal scale, we can say, okay, we are interested in 1,000 kilometer scales. That's our the scale of the cyclones that we are interested in. But really, velocity scale, we have to essentially take observations to use this. Or we say we define a time scale that is 1 day, then we would also come to this velocity scale. But essentially, it's not a rigorous scale analysis, because we have to put in something that is not really given to us, but we have simply to observe. But it helps us to understand which terms are important. So the typical velocity scale in meridional or zonal flow, doesn't matter, we call this just a scale, is about 10 meters per second. That's the typical velocities we have outside in the free atmosphere. Can be 20, 30, can be less, but this is typical. The vertical velocity, it turns out, again, you have to measure it, is very small compared to this. It's just 1 centimeter per second, so 10 to the minus 2. The length scale, okay, is something we have seen already. The cyclone scale, thousands of kilometers, let's say 1,000 kilometers. Vertical is easier. We can say, okay, the height of the tropopause will give us a good indication of where we are in the first, to a first degree, we want to stop our analysis. Although, in reality, that's not the case. There are interactions between the stratosphere and the troposphere which are very relevant for all kind of dynamical things, also for extended range predictions and things like this. But to a first order, let's say we can restrict our consideration to the troposphere for our analytic analysis, if we want to. Typical pressure perturbations, again, we have to make a measurement. 10 hectopascal is a typical. Density itself, okay, we can, that's about 1 kilogram per cubic meter at the surface, but then of course it changes with height, it becomes smaller. But more or less, okay, maybe that becomes, if we go to 5 kilometers, it's only half of that. But that's the scale. Relative density perturbations are in the order of 10 to the minus 2. So that's a generally the case. All the variations that we look at are small compared to the mean quantities if it comes to thermodynamic quantities. The temperature perturbations will be in the order of 10, 20 degrees, but we compare them to the absolute temperature of 280 degrees. So again, much smaller. This leads us, this length and the velocity scale leads us to a time scale. So we can prescribe either this time scale or the velocity, given that we have this length scale fixed. And that is about 1 day. It's a typical time scale where things do evolve in our large scale, in this case extratropical flow. The typical magnitude of the Coriolis parameter is 10 to the minus 4. So that's because F is equal to 2 omega sine phi. Let's say, okay, this is mid-latitudes. Less than 1 is a half or something that goes out with that. So we just have to consider omega is 2 pi over 1 day, so 86,400 seconds. So that's 10 to the 5, so let's say about, it's correct to say that then F probably is something similar to scales like 10 to the minus 4. That's one. And we have what we call the beta parameter, which is the derivative of the Coriolis parameter with respect to the meridional direction. And with similar arguments, then if you do this derivative, of course, here comes the cosine, and you have to divide this by the radius of the Earth. It turns out that then the scale of that would be 10 to the minus 11 in the mid-latitude regions. So if you insert this number to evaluate the vorticity, what you have to do in the scale analysis is you have to say, okay, vorticity scales as change of velocity divided by change of our length of our flow scales. So that's U over L, and that then becomes just 10 to the minus 5. So interestingly, this is one order, the relative vorticity is one order of magnitude smaller for our large scale flow compared to the planetary vorticity.
Excuse me, Professor.
Yes.
Since we have a minus sign, why don't we get a sort of cancellation? Since we assume the same velocity to both u and
Yes. Yes, this is just a scale analysis. It turns out in reality, actually, it turns out that the flow in the exotropics is mainly governed by a stream function. So they don't cancel out at all. They are very well organized in a way that there's no cancellation in this. We know the cancellation will be in another term that we will look at in a minute. So yes, there could be a cancellation and then this could be close to zero, but that's not the case. So that means also that the vorticity over the relative over the planetary vorticity scales like 10 to the minus 1, and this number that we see here, u over f naught, some kind of mean Coriolis parameter divided by the length, is called Rossby number. And if that is small, then we can say we consider like the large scale exotropical flow in our consideration. Because this also means, and this gives us the asymmetry for cyclones and anticyclones that are different from tornadoes. Tornadoes rotate like, even though this is being discussed, but they rotate cyclonic or anticyclonic as the randomness describes, or like the water in your bathtub rotates anticyclonic or cyclonic. It doesn't matter. But on the large scale, that's not the case because of this asymmetry. This divergence term is mainly governed by f times the divergence instead of planetary vorticity times divergence. It's not exact, but to a good order of magnitude. So that gives a directional. That means whenever we have a convergence, we create positive vorticity. Whenever we have divergence, we create negative vorticity. That's the asymmetry that comes into play for the large scale. Then we can make further. We can do this game for all the terms. Just insert numbers naively. We have everything is provided, so we can do this. Whenever we see something like this, it's the magnitude of W divided by the length scale and so on. It's very simple to do this. You can verify this as a homework. And we come to result essentially that the outcome of this analysis would be the divergence is equal to 0. Because there's no other term that can balance the divergence. It's the largest term here. And this means, yeah, we have made a mistake. When we estimate the divergence by U over L, that's not the way the divergence scales. Because I explained to you, it turns out that the flow in the exotropics is mainly governed by a stream function. So it's mainly rotational. So the divergence, there is divergence, which is important, but it's one order of magnitude smaller than the vorticity. So it turns out this divergence term, there is a cancellation between the two, a systematic cancellation. If we purely consider the what we call geostrophic flow its divergence is 0. There's a systematic consolation. And therefore, the estimation of this is an overestimation. So our divergence doesn't scale like the vorticity, like we would estimate as 10 to the minus 5, but it scales as 10 to minus 6. That, again, we can derive from observations, but even knowing that our flow is mainly geostrophic, this is the outcome. And with that, then, okay, we have terms that balance. So then the important terms would be, let's go back. The terms that have the same magnitude would be the advection terms. This advection of planetary vorticity, or beta effect, and the divergence term. Whereas these terms are, maybe you wouldn't want to neglect them in a weather forecast or in a climate forecast, because if you can do it, you want to keep these terms. But to first order understanding of what is happening in the cyclone or anticyclone, we can say these terms are definitely one order of magnitude smaller than the other. So what we get in the end, also the vertical advection term, of course, turns out to be small. So what we get is this equation here, where the dH by dt just collects the horizontal components of the total derivative. This is our first order approximation of our vorticity equation. And this clearly tells us whenever there's convergence, we get positive vorticity. We don't know yet if that will be positive relative vorticity or can be translated into a change of the Coriolis parameter. But let's say one interpretation would be, in order to spin up the cyclone, we have to have convergence. In order to strengthen an anticyclone, we have to have divergence. That gives us the basic asymmetry, because things change from the northern hemisphere to the southern hemisphere because F changes also sign. Okay, we have discussed this now, so now we want to derive the potential vorticity conservation, which can be derived from this equation that we have just derived. So what we have to do is we have to use the continuity equation. Now, how does the continuity equation strictly look like? The equation for the density of our flow. Minus rho divergence, right? That's our continuity equation. Now, and this equation would be the correct equation to use in the atmosphere. Now we are using our hammer again and say, okay, this is much too complicated. A good approximation, even in the atmosphere, is to say that the variations of density are small compared to the variations explained by this term. So as a first order approximation, we can use that the three-dimensional divergence of velocity is equal to 0. So that leads us to this equation here. And with that, we are kind of in our model framework, we are in what we call incompressible model. So the density is kind of treated as if it was constant to some approximation. But that also means so we consider now a kind of really what we consider as a fluid, where we have some kind of height of this fluid. But the height could be a free surface. So the height of this will be governed by the convergence, the local convergence in this region here. So whenever there's local convergence, the height has to go up, and vice versa. And what is also assumed is that this flow is barotropic. That means that the horizontal velocities that we have in this flow are assumed to be not a function of z. So they are not the function of z. And we assume that that's constant. That's called shallow water approximation. And okay, so we use this. So first of all, we replace in the divergence term of the vorticity equation, we replace that by minus dw by dz. And then we integrate this equation from the surface, which can have an orography, so a varying surface or topography, to the top. But for the velocity components here, they're all independent of height. So that integration is trivial, just gives us the height, that integration on this side. Whereas on the right-hand side is also trivial, because since we have dw by dz, we integrate that with height, means that we get the vertical velocity at the top minus the vertical velocity at the bottom, multiplied by the vorticity. Actually, we have reduced essentially for the beauty of this equation, we have inserted again, instead of just f plus psi, which is the more correct, exact form here. And now we can make use of this, what we call geostrophic approximation, because let's go back to the horizontal equations of motion. So which terms in this equation are governing the geostrophic balance? Coriolis and pressure. So it turns out if you do a first order scale analysis, we will do this actually later in this course. If you apply that, you can insert the same numbers actually. In this equation, let's see, u, that's 10 to the 2 divided by 10 to the 6, 10 to the minus 4. And here is 10 to the minus 4 times 10. So this is 1 order of magnitude larger than the advection terms. So you can, using the same kind of scales that we have posed there, you can show that the first order approximation in this equation is this geostrophic balance equation here. But that applied to a system where actually, and you will do this as a homework, where the pressure changes, let's say horizontal pressure changes within the system, can be just explained by variations at the height of the top. That's a property of the hydrostatic equation, if you integrate that vertically. That means that you can replace these pressure differences here in this simple barotropic model by horizontal changes of the height. So this horizontal pressure gradient can be explained by the horizontal gradient of the height of our medium. Okay, so that's the basis for example, this equation here. Our geostrophic balance is explained by 1 over f naught vertical unit vector cross product with the gradient of phi, where phi is the g times h, g times the height of our system. We use here f naught, a constant Coriolis parameter, because we assume our flow remains close to some base point in the meridional direction. This guarantees that the geostrophic wind has zero divergence. So all the divergence is from the non-geostrophic part of the wind. If we have a varying F, that's not exactly the case. So if we insert this here, then you can derive easily that the vorticity is just the Laplacian of the height field. So with this velocity expression for the geostrophic wind, you can derive this. And you will derive this relationship in an exercise that you can use instead of the pressure horizontal change. You can use the change of the height of the system here, multiply times g. And using that, this means we can close our system of equations is closed actually. The beauty about having this additional constraint of geostrophic balance is that we have just one equation, which is the vorticity equation, and everything else can be derived from this equation. We don't need any other information. There's no coupling with anything else. So this equation is a completely closed system of equations. And so you can see that this can be easily integrated. So we have 1 over absolute vorticity times change of that, and 1 over the height times change of that. So that's explained by the logarithm. And then if the logarithm, d by dt of the logarithm is constant, is 0, then also the d by dt of the argument itself is 0. So we have the conservation of this quantity, absolute vorticity divided by the height of our system. So whenever the height is changing, something has to happen to the vorticity. It has to be spinning up or spinning down. It's a very powerful relationship. Particularly, this is so powerful if you think of air flowing over mountains. So as soon as air is flowing over a mountain, you know that something has to happen to the vorticity. It's not just going over there and nothing has happened. Something has to happen to the vorticity. This relationship can explain a lot of the cyclone developments in this region. Because if air is flowing over the Alps from the north side, then on the southern side of the Alps we get, no, you will do this in an exercise because of the way the orography goes, there has to be cyclonic vorticity on the southern side of the Alps. And we get typically, with northerly flow, then lee cyclone developments on the southern side of the Alps. And this is the same is true for all other mountains, depending on the flow direction. And can be simply explained by the fact that as the air flows against the mountain, then let's say if we assume that the flow is squeezed between the orography of the mountain and the tropopause, that has to squeeze down, then it spins down, but then as the flow expands, it has to spin up and the vorticity has to increase. So whenever this is decreasing, this has to decrease. Whenever this is increasing, this has to increase. So, to the south of the mountain, we increase the height of the flow again, and the vorticity has to spin up. A very powerful mechanism. Yeah, this explains some basic features of the flow wherever we are. There is actually in that version of the equation, that is not yet a closed system of equation, only if we have a good estimation for the height of the flow. But otherwise it's not yet a closed system, depends. But it turns out that even a simpler equation is often valid if we are in the atmosphere without orography, just over, let's say, over the oceans. It's not exact, but the first order approximation is that then we have the conservation of the absolute vorticity. D by dt xi plus f is equal to 0. And this actually can explain the movement of air parcels in these Rossby waves that we have already given a name. We will derive their dispersion relationship later, the exact dispersion relationship that explains how they propagate and how the energy propagates and so on. But if you assume that we have a line of constant pressure, let's say, or height of our system, and maybe here we are in a trough and here we are in a rich region. So let's say the air is flowing out of this trough. The vorticity here is positive. It's rotating cyclonically. We go to the north. As we go to the north, according to this law, so F is what is happening. If F goes to the north, F is increasing. Right? F goes with the sign of the latitude. That's increasing. But if that's increasing, then according to this law, the vorticity has to decrease. So it has to prescribe a negative vorticity. So with this kind of basic principle, we can explain the movement of our air parcels in these waves, large-scale waves, which we call Rossby waves, for which we will maybe next lecture, the lecture after that, derive the dispersion relationship, how these waves actually move and not the air in the waves. So the beauty about this equation now is if we use this geostrophic balance, then the system, this equation here gives us a closed system of equations. System of equations means just one equation. Because we can express everything here in terms of either the height or equivalently the stream function of the system. So if we define the stream function as g times h over f naught, then that is the stream function, and then the equation looks like this. Or stream function and height would be equivalent here. The same equation would be valid. You can multiply this all by g and f naught, divide by f naught, and then it's also an equation for the height of the system if you want. So it's the same. So we have one equation and just one variable, because everything here, even this horizontal operator, derivative operator, we can explain the velocities by the stream function, d psi by dy and d psi by dx. This equation will be used by us to derive the dispersion relationship of Rossby waves later on. And it's actually, this equation was the first equation that has been used to do a weather forecast. Very simplified. Essentially thinking of that this governs the flow in the mid-troposphere. They have tried to find initial conditions for this case, for some case in Europe. And it was Richardson actually who tried to integrate this equation 100 years back, nearly 100 years back in the past, on a piece of paper. And it turned out the solution was completely wrong after one day. The observations were completely different. But his calculation actually was correct. The problem was with the way, there were waves, unbalanced waves that were destroying essentially his solution. But his calculation was correct. But nowadays, it's still, this equation can describe nicely the evolution of the extratropical flow for a few days. Eventually you have to take other terms into account. But maybe for 1 or 2 days, if we observe, you make a measurement of the atmosphere, you observe the wave structure, and you could try this equation, let's say at the 5 kilometer height level, to predict how these waves propagate. And we will look at this in the theory a little bit by considering the dispersion relationship by these waves. Essentially, as you can imagine, these waves propagate depending on mean flow and other characteristics. Now, to make things a little bit more complicated, now this is a very nice law, but we had to make a lot of assumptions to get to this. We had to have this shallow water assumption, and then still we can derive something for the atmosphere. But of course, there's a more generic conservation law for the atmosphere, and it's essentially only a basic mathematical manipulation of the equations of motion from which that can be derived. It's very generic potential vorticity conservation law following the motion. That's a powerful thing about this. This is a conservation law following the air motion. It's a very, very interesting conservation law. It's not just a global conservation law, but it's a conservation law. We follow the motion. So the derivative goes like this. You write down the Navier-Stokes equations. Let's see if we can still recall the terms here. So this is, we know, is the advection term, right? Pressure gradient term. What is this? Coriolis term. This is now three-dimensional, U, V, and W. What is this term? The gravitation. And this is we use as an abbreviation for our frictional forces. You write them in a way, okay, you can derive this, could just write it as a vector f, doesn't matter. Now, from this equation we can derive the general vorticity, the equation for the absolute vorticity in a generalized way. You will do this as homework. Of course, you have to apply the three-dimensional rotation to this equation and do careful manipulation of that equation. The final result is this. You get an equation like this. One trick is, of course, you can be done by applying properly vector algebra, but you can also simply use Cartesian coordinates and do it for the components of this equation. And then you will find it can be expressed in this way. So this omega in this equation here is a constant. This is just the rotation vector of the Earth, but its component on the Earth's surface are actually not. That makes the situation a little more complicated. Using the continuity equation, you can rewrite this vorticity equation in this form. You can just use the full continuity equation to rewrite this a little bit. And one term gets lost, actually. One term gets eaten up by this total derivative that is now also acting on the density. So there's one term less in this equation because it's hidden here. And now comes a trick. Ayrton has derived this law. He used this trick. Imagine there's a quantity. Of course, he had some quantity in his mind. A quantity that just depends on density and pressure. Could be any quantity, but the good thing is for one component gas or fluid, that can be any thermodynamic property. So that could be temperature, potential temperature, entropy, whatever you want. It turns out that then, in the end, you have to pick the thermodynamic quantity that fulfills some particular law, but for the time being, you could take any thermodynamic quantity. Lambda. We call it lambda. It could be temperature or whatever right now. But it doesn't matter. We can keep it open. So then the general evolution equation for this could be d lambda by dt, total derivative of lambda is equal to some sigma lambda. Under sigma lambda, any other terms could be hidden there. So this is a general evolution balance equation for this quantity lambda. Of course, if lambda is a conserved quantity following the motion, then this sigma would be 0. And that's the important and interesting application of this. But that's not the case for any thermodynamic quantity. A simple calculation, I say, okay. It's always dangerous to call something simple calculation, but in the end, you want to evaluate this term here by inserting this term here. That means that you have to change these two operators, but then an additional term comes up, because if you take this term outside here, then you have to take into account that this then applies also to this operator, so you have to subtract that one here. It's very easy to do. Maybe you can do it as an exercise. If not, we will discuss this in the next exercise. Okay, you try to derive this equation. Okay. I suggest you do it in Cartesian coordinates, where express this as the scalar product in its components, and then it's a very basic manipulation, and eventually you have to insert this here. Try to do this, please. It's really straightforward to do once you have written it down. And then on the other hand, we can multiply the vorticity equation, this slightly modified vorticity equation, by the gradient of the thermodynamic quantity lambda. And then everywhere we multiply the scalar times gradient lambda, times gradient lambda, times gradient lambda, frictional force, sinusoidal term, and this additional term. And of course there was a meaning. The meaning is that, if we add these two up, now they eliminate each other. Divide this by 1 over rho, and add these two equations up, and then this term and this term build the total derivative of just one term, which is this. And the only remaining terms, this term goes out. The only remaining terms are this term here and this frictional term here. So that's the final balance equation for this strange quantity here. Now, we want to identify cases where this is a conservation law following the motion for this quantity here. First of all, if lines of constant pressure and lines of constant density are parallel, then this cross product vanishes. That's a simple case. But it's enough, since we use this trick, to multiply this by gradient lambda. And that's probably one of the nicest thing about this trick, is that then the gradient of lambda can be expressed as d lambda by dp gradient p plus d lambda by d rho gradient rho. But that means that this cross product is perpendicular to gradient rho and to gradient p. That means that with this completely vanishes. All terms in this equation vanish identically. No further approximation. This is gone. But we are still left with these terms here. So what we need additionally is that our quantity lambda is a quantity conserved following the motion. Then this term vanishes. And that our flow is frictionless. Then this term vanishes. So, for this to be valid, we have an interesting choice, because we could choose lambda to be the entropy. entropy is not you know the entropy is increasing in a closed system, so the entropy is not a conserved quantity. But for many of our applications for large-scale flow, it's a good assumption to assume that the entropy of the flow following the motion is conserved. It's a very good first-order approximation, even for convective events. That assumption is often made. So to use the entropy, or equivalently, that is what will be done, the potential temperature, there's a 1-to-1 correspondence for the atmosphere, is a good choice, because that quantity is for, if we name it adiabatic reversible processes, is conserved. And if a flow is adiabatic reversible, it should also be frictionless. In that case, we can derive this, if these are fulfilled, exact conservation law following the fluid motion for this quantity here. This quantity then is called potential vorticity. Oh yeah, for the ocean I think they use potential density as the thermodynamic quantity. Anyway, for the atmosphere then, if you pick theta, the potential temperature, which is related to temperature and pressure, or density and pressure, any other two thermodynamic quantities, if you pick that, and we know that for a large-scale motion, actually the vertical component of the absolute vorticity is the most important one, governed by the horizontal velocities, then we get just Q, to good approximation, d theta by dz times theta plus f, absolute vorticity, divided by the density. This is now our potential vorticity in that case, approximately.
That's the Z component.
That's the Z component. Because it turns out that our absolute vorticity vector is mainly governed by that component. And also, the vertical gradient of potential temperature is much larger than its horizontal gradients. So the two components are actually maximized for this vertical component. But no, this is an approximation. We don't necessarily have to do this. And this is actually, okay, that's this here. This is called eta, of course. We call it sometimes eta, the absolute vorticity. So this we will evaluate later in this course in the pressure coordinate system. Because at the moment it looks still a little bit complicated for the atmosphere. We have still the product of three quantities. Here is the absolute vorticity, which varies, the density, which in the real atmosphere varies, and the gradient of potential temperature, which varies. So it's a triple product. But in the pressure coordinate system, it turns out that this density is getting eaten up by derivatives. So this becomes simpler in the pressure coordinate system. And then we will try to interpret that a little bit. Now, of course, people have asked the question, okay, how can you go back from this general conservation law? How can you go back to this barotropic potential vorticity conservation, which is just the height of the system, absolute vorticity divided by the height of the system? So there is a way, if you define lambda like this, and for the barotropic flow you don't need any other properties than this, because barotropic flow already means that density is constant, so the sinusoidal term vanishes already itself. And it turns out that this is also conserved. This relative height of our parcel with respect to the total height of the system is a conserved quantity, and if you insert that in the general conservation law, it turns out that yes, So this explains, this gets back our barotropic vorticity conservation. So things are consistent. There's a way to go from the general conservation law back to the special conservation law.
Excuse me, can we write that lambda as a thermodynamic? That's a combination of thermodynamic quantities.
I think so. I have not tried to imagine anything different from potential temperature or equivalently entropy. You could pick temperature, but then the problem with temperature is not a conserved quantity for adiabatic reversible
I
flow.
was referring to the last example, just to recover the case of the barotropic flow.
Yeah, this equation is enough. This equation gives you the absolute vorticity divided by the height of the system. If you know, the gradient of this is just 1 over h, and then you go back to that equation. But you know, in principle, probably I think people may have tried to pick other thermodynamic quantities. In fact, for the ocean, it turns out, you know, you have to pick something that is more equivalent to the entropy, which is the potential density. And so for the ocean, that can be a different quantity than potential temperature. But yeah, maybe in principle you could try to see what's happening if you pick any other quantity and if you can learn anything from that. But the general use of this is taking potential temperature for the atmosphere. If you have a special flow case where something else is conserved, you may consider to take a different thermodynamic quantity. But I'm not aware. So that brings us to the exercises. They should be all straightforward. They're mostly just reproducing what was done during the lecture. For here, so this is the geostrophic law that you know already well, right? But how do we eliminate the pressure? Think about that. You essentially you have to integrate the hydrostatic equation from an arbitrary height in our flow to the top where the pressure is assumed to be 0. That's the trick. And then you can replace this horizontal gradient in pressure by the horizontal gradient in the height of the system. Then the exercises 4 and 5 are taken from the Halton essentially. They are just inserting some numbers, which can be good sometimes. So you assume that you are somewhere with a certain amount of vorticity, then you are moving some north or south, so what is happening to it, work that out. Just applying the conservation of absolute vorticity here. In the case of 5, the conservation of potential vorticity, for assuming a very simple situation. You assume that our fluid is rigid at the top, but there's an orography where it moves over, and then let's see what's happening to the flow if we move to the north, and so on. How is the vorticity changing? This is just a simple derivation, and this is just 7 is just repeating of the conservation law for the absolute vorticity. So maybe in the next lecture, if we have problems with some of these exercises, we will do them on the blackboard. Okay. Like in all other courses, I assume, the rule is that these exercises are relevant for the final exam. Okay, so in the end, we better capable of doing the exercises.